This is lesson number 11 presented on March 8th or March 9th. This video will talk to you about the domain and range restrictions on exponential and log functions, as well as the properties of logs. You will follow this up with an exit test and a warm-up assignment. Let's take a moment and just do a gratitude check. Think about 2 positive things that you have been able to do or achieve from being online school, and 1 that you missed when you were in the building. Again, for me, it would be being able to spend more time with my daughter and make sure I'm making a commitment to my health. The thing I miss is seeing faces and doing group work. On Thursday and Friday, we started talking about the relationship between exponential and logarithmic functions. What we see here graphed in blue is the exponential function of y equals 2 to the power of x. The domain for all exponential functions is all real numbers. And your range is y is greater than 0. Again, we use the parenthesis because we have a horizontal asymptote when y equals 0. When we start talking about transformations with exponential functions, it is the location of the vertical shift that's going to affect the range and allow us to calculate our range restrictions. The inverse of an exponential function is a logarithmic function. So this one graphed in purple is log base 2 of x. The range from the original is the domain of your inverse. That means that log functions have a domain that is restricted. The domain from the original is the range of your inverse. That means the range for log functions is all real numbers. Instead of having a vertical asymptote, a horizontal asymptote, we have a vertical asymptote when x equals 0. Thinking about those transformations again, log base b of x minus h plus k, it's going to be the horizontal transformation here that affects the domain. Again, similarly to how the vertical shift affected the range on an exponential. So let's look at 3 examples of exponential functions, talking about what their range would be, again, going by that vertical shift. The first function has a parent function of 2 to the power of x. And we can see that that graph was reflected over the x-axis and shifted down 4. The combination of those 2 things is going to affect your range. Because this has been shifted down 4, the location of your horizontal asymptote happens when y equals -4. This graph was reflected over the x-axis, which means the function is below the asymptote, and your range is from -infinity to -4. The second function has a parent function of e to the power of x. And remember, e is about 2.7128. It is an irrational number stored in your calculator. This function has been shifted 3 units to the right and 5 up. That means the location of your horizontal asymptote is at y equals 5. And this graph is above the asymptote, so your range is y is an element from 5 to infinity. Again, we want to make sure we're using parentheses here so we acknowledge that horizontal asymptote. The third function has a parent function of 1/3 to the power of x, or you can think about that as 3 to the power of -x. Something that has a 1/3 power is the same as a base of 3 with a reflection across the y-axis. Now, whether this is growth or decay reflected across the y, that will not change your range in your horizontal asymptote. We still really just care about that vertical shift. So here, based on that vertical shift, it's moving down 5 So your horizontal asymptote is at y equals -5. Again, this graph, whether it is growth or decay, will still be above the asymptote. So your range is going to be from -5 to infinity. For our next three examples, let's look at the inverse of those functions, which in this case is logs. For logs, it's what's inside the parentheses following the log that is restricted. What we know is that the domain of log functions has to be greater than 0. So whatever is in the parentheses has to be greater than 0 in order for us to find our domain. So for this first function, I'm going to set that x minus 4 greater than 0 and solve for x. This is going to give me my domain restrictions. Add 4 to both sides, and we see that x is greater than 4. That means your domain is x is an element from 4 to infinity. Again, think about this if you want in terms of your vertical asymptote. That vertical asymptote, because of that horizontal shift, will happen at x equals 4. So your graph is going to be to the right of that function. Looking at the second example, I have log of -3x plus 4. Again, whatever is in the parentheses has to be positive, even if that is a larger linear term. So for this function, I'm going to set it greater than 0. Move the 4 to the other side. Divide by -3. And remember, when you divide by a negative, you flip the direction of your inequality. So what this actually means is that you would have a graph that has been reflected over the x-axis, and your domain, over the y-axis, your domain would be from -infinity to 4/3. And your graph would be completely isolated to the left of your vertical asymptote. If we wanted to find that vertical asymptote, again, we'd be looking for where that function is equal to 0. And that would give us the location of the vertical asymptote. Would be at 4/3. This graph would be reflected over the y-axis and be to the left of your vertical asymptote. For example 3, again, whatever follows the log has to be greater than 0. This is a quadratic inequality. Again, we dealt with this in chapter 3, as well as in chapter 4 when we were dealing with some of our rational functions. I need to figure out where this quadratic is greater than 0. Start by figuring out when it's equal to 0, kind of again by factoring. We've done factoring a lot to understand how that one works. We're going to have an x-intercept at 0 and an x-intercept at -2. This is a positive parabola. So kind of doing just a quick sketch of the graph again, looking at where that inequality is greater than 0, and that would be in between -infinity and -2 in union with 0 to infinity. So in order to find our domain restrictions for a log function, even if it's not a simple transformation, anything that's in the parentheses gets set greater than 0, and you solve for x. That x is going to be the location of your domain restrictions. As we move from looking at the graphs and the domains of logs to looking at the properties of logs, remember that exponential functions and logs are inverses of each other. That means their properties should feel very similar. These are our properties of logs. Product property says if a log base b of m times n, if you want to expand that log, you write it as log base b of m plus log base b of n. If we are expanding, we go from the left to the right of this rule. If we're writing it as a single log, we go from the addition back to the multiplication. And again, this should make sense to us in terms of exponents. If I had 2 to the power of 3 times 2 to the power of 5, I would have the same base, and I would add those powers together. And again, we can think about this just like we think about the logs. If you have two logs with an addition, you want to write them as a single log, it ends up being a product. The quotient property again, and you're writing it as an expanded log, it's log base b of m minus log base b of n. And if you're writing it as a single log, you write it as a quotient. Again, very similar to our exponent rules. If we had x to the fifth divided by x cubed, those have the same base. The quotient turns into subtraction, and then I simplify from there. So again, we should be able to see the correlation between the quotient property of logs and the quotient property of exponential functions. The power property is a little bit different. When you think about the power property, it's saying log base b of m to a power of p ends up being p log base b of m. So that power ends up being your coefficient. Okay. This one is a little harder to draw to a direct exponent rule, but I think when you think about it, that p is the quantity of chunks of that log base b of m. So that's why you can kind of think about it at the beginning. Again, make sure as you guys are writing this down that you're pausing the video and you're writing down the notes in your own time. After you get the notes and you feel like you understand the properties, then you want to replay the video and move on to the next part. Let's practice some of these logs. All of these are written as expanded logs, and I'm asking you to write them as a single log. Again, first step is to make sure the base is the same. On this first one, it's addition, which implies multiplication. So as I write this as a single simplified log, again, the base does not change. It's still base 10. I would take x squared times y cubed to write it as a single log. On the second one, log base 3 of 18 minus log base 3 of x cubed. Again, that subtraction implies a quotient. So as I write this as a single log, I'm going to write log base 3, the base doesn't change, of 18 divided by x cubed. And I cannot simplify that any further because of the 18 and the x, so that would be my final answer. On example 3, I have 2 log base 5 of x. That exponent, as I write it as a single log, goes up to the power, and this becomes log base 5 of x squared. Now, sometimes we have to combine these rules in order to be able to write this as a single log. So on example 4, that 3 is at the beginning. So that 3 needs to go to a power of 2x. That subtraction implies a quotient. And again, that coefficient of 3 needs to go up to the power. So as I write this as a single log, again, my base does not change. It's log base 2. The numerator is going to be that 2x cubed. The subtraction implies that there's a quotient. And then in my denominator, I'm going to have x to the 9th because I would have 3 times 3 in the power. If I want to simplify that a little bit, I could have log base 2. 2 cubed is 8, so I would have 8x cubed divided by x to the 9th. And again, here's where those properties of exponents come in. We see that we have 3 x cubed in the numerator and x to the 9th in the denominator. Therefore, we could simplify this a little bit further to 8 log base 2 of 8 divided by x to the 6th. Again, when you have x's in the numerator and denominator as a quotient, you subtract. So now we're putting those quotient, the log rules together with the quotient rule and the power rule, and we're using some of our exponent rules in one problem. For the next example, again, that power of, or coefficient of 2 needs to go to the power. That coefficient of 3 needs to go to the power. and addition implies multiplication. So as I try and write this as a single log, it'd be log of 2 squared times 2 cubed. Again, I would want to simplify that exponent as I see it in the parentheses. Same base means you add the powers together. So you would get log of 2 to the 5th, and 2 to the 5th is 32. Now the last example, again, has several rules. I see a 2 at the beginning of that log. That's going to go to the power in the x. The 3 is going to go to the power of the z. That is addition, so that would become multiplication. Then I have a 4 that needs to go to the power of the w, and that is subtraction, which is going to imply a quotient. So as I write this as a single log, it's going to be x squared z cubed in the numerator divided by w to the 4th. Again, the coefficient goes to the power, addition implies multiplication, subtraction implies a quotient when we write it as a single log. Now there is nothing I can do here to simplify. The next rule we need to know is the change of base. We talked on Friday about how, or Thursday as well, how the common log is your base 10, which is when we drop that number. And we talked about how your natural log happens when you have base e. Now those are the only two that your calculator has stored. So if we want to evaluate a function, we have to convert it either into base 10 or base e in order to evaluate that in the calculator. Now on the first one, again, we should kind of think about what this would be as an exponent. I'm missing that exponent, so I should be able to say 2 to the power of what equals 64. And we just had that example that 2 to the power of 5 is 32, which means this should be x equals 6. If I want to evaluate this in the calculator, though, I would type this into the calculator as log of 64 divided by log of 2, and that will also give me an answer out of 6. If I wanted to put this in a base e, I could have done natural log of 64 divided by natural log of 2, and that would have also given me 6 if I evaluate in the calculator. This one was exact, so we should be able to recognize these base 2 and base 3 functions. If we can't, again, no big deal, we type it in the calculator. As you type it in the calculator, after you type the word log of 64, make sure you put the parenthesis on the end of the 64 before your division, or else you will not be able to get truly log of 64 divided by log of 2. So watch where your parentheses are to make sure you're ending the numerator before you divide. Problem 2, or example 2 on here is log base 2 of 5. So we're saying 2 to what power equals 5? Well, we know 2 squared equals 4, and we know 2 cubed equals 8. So we know that our value of x is going to be greater than 2, but less than 3. And again, the way we type this in the calculator is we would do log of 5, parenthesis on the end, we make sure you separate that out, divided by log of 2, and that's going to give us the decimal equivalent of that function. For our next example, we have log base 3 of 8. Again, you're looking for that solution. So 3 to what power equals 8? We know 3 squared equals 9. So when we actually evaluate this, it should be a little bit less than 2. So I would put this in my equation. Again, log base 8 divided by log base 3. Or I can put it as a natural log, and it'd be natural log of 8 divided by natural log of 3. Once you get that, again, make sure as you type it in the calculator that you close the numerator before you do the division, and you should get about 1.893. On the last example, again, let's think about this fraction of 1/25. I can use my negative exponent rule to write this as 25 to the negative first, and we know that 5 squared is 25, so this fraction is the same as 5 to the negative second power. So when we're writing this out, we're looking really to evaluate log base 5 of 5 to the negative second, and again, we're looking for that power. So if I switch forms, it'd be 5 to the power of x equals 5 to the negative second. Again, base is the same, powers have to be equal, and we would get x equals -2. We could again evaluate that in the calculator if we wanted, but it's nice to use a little bit of logic here as we are solving these problems. Okay. All right, that concludes lesson number 11. The exit task is open. Once you complete the exit task, you want to move on to your WAMAP assignment. Again, thank you guys for understanding and watching the video, and we will meet again on Thursday or Friday.